Good afternoon on our fourth and final day of these 2021 AMS Washington Forum. I'm super excited about the next keynote. It's the Ocean Enterprise keynote on the new blue economy, and somebody that we all know and love, Dr. Rick Spinrad, will be providing this keynote, and I'm going to kick it over to Pam Ench. Pam, all you.
Hello, everybody. Thanks very much, Jen. So welcome to this afternoon portion focused on oceans and the blue economy. This Ocean Enterprise keynote talk and the session that follows were organized by one of the newest committees within the AMS, and that's the Ad Hoc Committee on Oceans, Coasts, and the Blue Economy. Initiating this committee is just one of the ways in which AMS is working towards the goal of strengthening the communication and increasing the dialogue between the oceanographic and the atmospheric science communities. I'm the chair of that new committee, and my co-lead organizer for this portion, Dr. Ralph Rayner, is one of the members. Just a reminder here, before we start, if you have any questions during this portion, as usual, please put them in the chat and also note your affiliation. And now it's my great pleasure to introduce our keynote speaker, Dr. Rick Spinrad. This is a name which has come up a lot the last several days, both in terms of his phenomenal background and the roles he's had, but also he's been mentioned as a mentor to several people. So again, it's just a great pleasure to introduce him. Dr. Spinrad is a professor of oceanography at Oregon State University. He's a member of the Ocean Studies Board of the National Academies of Sciences, Engineering, and Medicine, and he's vice chair of the U.S. National Committee for the Decade of Ocean Science for Sustainable Development. In 2016, he retired as chief scientist of NOAA, and from 2003 until 2010, he was the head of NOAA's Office of Oceanic and Atmospheric Research and the National Ocean Service. Prior to joining NOAA, Dr. Spinrad held leadership positions at the U.S. Office of Naval Research and the Oceanographer of the Navy. And he's had many other roles in addition to that. But most recently, some of you may have heard, just last week, he was nominated by President Biden to be the next NOAA administrator. And with that, I'd like to send it on over to Dr. Rick Spinrad.
Thank you, Pam. I really appreciate that introduction. In fact, I was so excited about this that I went out and had rotator cuff surgery. So those of you who are wondering why I'm bound up, that's what it is. Let me point out that I am really excited about this opportunity. I've found the AMS DC Forum to be one of the really exciting events. Every year I was back in DC, I tried to attend, so I'm delighted AMS has been able to set up this virtual forum. And today I want to talk about the subject of the new blue economy in the context of where we're going and how actually we've built on a lot of the historical developments within the meteorological community. If I could have the next slide, please. To start, let's look at what a succinct definition of the new blue economy looks like. I'm not going to read it to you, you can all read, but the important thing to realize is that this is an information and knowledge based economy. So the currency of the realm really is bits and bytes of information. But of course, next keystroke, there has to be an overlay of sustainability, misspelled sustainability, I might add. I'll say a little bit more about that in the slides to come. So let's talk a little bit more about the details of the new blue economy. Next slide, please. In its most simple form, and you're going to see various versions of this kind of flow scheme, if you will, from subsequent speakers. But basically, we're talking about taking fundamental data, observations through programs like the Global Ocean Observing System or the US Integrated Ocean Observing System, providing that to intermediaries who develop value-added products, and I'll talk a little bit more about who those might be, to the end users, if you will. And those can be managers, planners, developers of value-added products. Next keystroke, please. The important thing to realize, however, is that there are a number of overlays that directly influence and are influenced by this value chain. what regulations and policies control the flow of information? How does R&D advance capabilities? And of course, do we have the people to work this? And again, I'll say some more about that in a minute. But next slide, let's talk about a very specific example. And I'm going to take this from the meteorological community. And it's an example that I think the AMS membership and the participants in this activity today will be very familiar with. Next keystroke. So from the National Weather Service, you're apt to get a surface analysis like this that shows you pressures and also shows you radar reflectivity, giving you some sense of what might be happening. But this is not necessarily what the end user can take advantage of. They don't know how to interpret this. So in come the intermediaries. Next keystroke, please. And in this case, I've chosen an example from our friends at AccuWeather, where they've taken the data provided by the Weather Service and built a value-added product that talks specifically about what the mix of different types of precipitation might be. Next keystroke, please. The end user in this case is the New Jersey Turnpike Authority, for example. And if you hit the keystroke one more time, you'll see that the information that comes out is that in this particular case, there's going to be severe thunderstorms, one more keystroke, and really the information, if you're a trucker, is that you're going to be facing gusts of 52 miles per hour. So we've gone from the most detailed and fundamental information in the surface analysis to a very specific recommendation, if you will, or decision aid for especially the truckers using the Jersey Turnpike. So next slide. This kind of capability is something that we have seen develop over the years in the commercial weather industry. And we've got many, many developers of these products and many, many different end users. So next slide. The question is, how about the ocean community? And I've chosen two examples of what I would call this emergent new blue economy. Mitch Roffer years ago recognized he could take NOAA data on sea surface temperature and convert it to decision aids for the tournament fishing community. And if you go to the Roffer's Ocean Fish Forecasting Service Incorporated website, you'll see that you can buy products specific to your ability to go fishing in these tournament fishing events. Similarly, and I think you'll hear a little bit more about this during the panel discussion, the evolution of operational oceanography to develop tailored products and services has really moved aggressively in Europe. And the Copernicus program is a great example of delivering those kinds of products and services. So next slide. The question is, why is it happening now? What has changed? What's emerging? What's giving us the capability to develop this new blue economy? And I would argue there are several things. Next slide, please. The first of these is the emergence of some extraordinary ocean observations capabilities. And again, you're going to hear some specifics on the panel about this. But just going from the lower left, you see the development of the Argos program, these floats that actually descend to about 2,000 meters, take observations of fundamental ocean parameters, ascend about every 2 weeks and send all of their data as a big chunk blast of information. There are now about 3,900 of these floats around the world's oceans, and they're already starting to give us great new insights. On the upper left, an autonomous, uncrewed surface vehicle manufactured by Saildrone is now providing observational capability, and I would add data telemetry capability in a way and in places on the Earth that we've never had before. In the upper right, it's just the Mike Freilich satellite that was recently put in orbit. We could spend the next couple of hours just talking about what the enhanced remote sensing capabilities are. And in fact, earlier this week, you heard some really good examples from some of our colleagues. And in the lower right, it's not just about platforms. The sensing capability has exploded. This is the Monterey Bay Aquarium Research Institute environmental platform, the environmental sensor platform, which basically measures DNA, resident DNA in the ocean. So we've developed just in the last decade some extraordinary capabilities for making observations, both more observations and more diverse observations throughout the full three-dimensional nature of the ocean. The next slide. The other thing that allows us to move forward with the new blue economy now is the extraordinary development in ocean modeling. In resolution, you see the NOAA GFDL MOM6 model 1/8 degree global resolution. A lot of that is made capable by computational capabilities. I've chosen to put in the middle slide an example of an extraordinary improvement in skill of forecast. It happens to be for the 500 millibar anomaly at 36 and 72-hour forecasts. I'd like to think most of the participants in this forum are well familiar with this kind of skill improvement, but one could look at just about any kind of ocean model and see similar sorts of improvement in skill. And in addition to the resolution and the skill, the diversity of parameters that are being modeled has gone up extraordinarily. Now, when I was a graduate student, of course, that was during the Jurassic, but when I was a graduate student, really all we were considering modeling was temperature and salinity in the ocean. Now what you see on the right is a model of aragonite saturation, basically a way of modeling ocean acidification. So not only do we have these extraordinary improvements in observations, we have these this incredible explosion in resolution, skill, and diversity of parameters that we can develop predictive models for. Next slide. The other thing that's changed is the level of attention. And you heard in Pam's introduction a reference to the U.S. National Committee for this new activity, the UN Decade of Ocean Science for Sustainable Development. While this is not a program in the traditional sense of having tens or hundreds of millions of dollars associated with it, what it does do, and you can see some of the specific language from the documents associated with the decade, is it provides a very high level substantiation and support and advocacy for developing a predicted ocean. Remember, this is something the UN General Assembly approved. This decade just started on January 1st. So we're going to see support at the highest levels of government for developing the information and knowledge that are the currency of the realm for the new blue economy. And finally, next slide, I'd say that the other thing that's giving us the opportunity right now is that the community, the professional community, is changing fundamentally. I'll say a little bit more about this in a few slides, but we're now looking at things like credentialing and certification, and also whole new training programs at a variety of level, at the community college level, at the continuing education level. So there's this surge of activity that basically validates, if you will, the professionalization of the ocean and marine technological community. Let me shift gears a little bit here. Go to the next slide, please. And I want to talk about a little bit of a retrospective. We've been thinking for many years in the ocean community about what kinds of products and services might be provided. This is a slide I've used several times. It's very detailed. It's not my intent to walk through it line by line, but to simply point out that you can see there are some examples from the past, like Deepwater Horizon and others, where there was an opportunity for specific new products. You can look through this. Mostly what I want you to get a sense of by looking at the use cases on the left side is that it's extraordinarily diverse. It deals with ecosystems, it deals with natural hazards, it deals with climate change. By way of just diving down to one example, let's go to the next slide, please. And I'll talk very briefly about this example. So I happen to live in Oregon right now. Oregon is one of the world's major producers and shippers of wheat grain. And to frame this for those of you who don't know the geography, what you see there is Oregon's coastline. And then in the inset in the lower right, you see that Portland, Oregon, where a lot of the grain is loaded around Portland, has a rather long run down the Columbia River to get out to the open ocean. There are about a dozen bridges. There are some shoals. I would point out that this is tidally influenced. I would point out that we tend to get a lot of rain in the Pacific Northwest, so hydrology, that is how much your vessel, if you could do the next keystroke, please, that this is a typical vessel that ships grain in Portland. You want to load out as much grain as you can, but you also want to make sure you're accommodating the buoyancy dynamics, given the changes in salinity, the tidal influence, the regional hydrology, how much precipitation we got. You want to get just under the bridges and you want to clear the bottom. So it's a really extraordinary challenge. And in fact, the next keystroke shows you the kinds of products that are being developed these days to predict both the salinity structure and therefore the buoyancy structure, as well as any changes to surface currents that you might have in the area. The ability to develop a predictive product that would tell the grain shippers, you can load another 2 tons of wheat as long as you leave port next Tuesday at 6 in the morning, is extraordinarily valuable. There's an open opportunity. So that's a detailed example of one of the retrospective potential capabilities for building out the new blue economy. Let's look forward. Next slide, please. What's changing? Well, even though I would argue this new blue economy has direct relevance to all of the commercial sectors that are traditionally part of the blue economy, if you look at what's happening in a number of sectors, there is abundant opportunity for providing a whole panoply of forecast products. The oil and gas industry, the energy industry, if you will, is looking extensively to renewables. Fisheries are looking to things like restorative aquaculture and sustainable capture fisheries. In the transportation, and I would add also relevant to the navies of the world, autonomous operations are becoming a much more important component of their portfolio. And then you look at the whole issue of coastal resilience, where there's a major discussion associated with the restoration economy. And in fact, the 30 by 30 parenthetical phrase there is shorthand for the global agreement to preserve and protect 30% of the world's oceans by 2030. So there's going to be a call for predictive products and services. So the next question is, how do we get there? Next slide, please. What do we need to do? And in this regard, I've talked a bit about some of these elements. I want to touch on all of them to a certain extent. Observations, product development, data stewardship, etc. So let's go to the next slide. We don't have time here to walk through all of this, but I think people can understand the issues of standards, QA, QC, continuity of data. These are all standard kind of issues associated with environmental observations. And they're certainly ones that I would argue have been part and parcel of the discussion of commercial weather industry development. I might argue that the last bullet here, the emerging new sensors and parameters, is one that perhaps is a little bit more abundant and obvious in the ocean community. I gave you the example of aragonite saturation, that is to say pH. I showed you the eDNA sensor. We are almost on a monthly basis seeing a new capability, a new parameter that can be observed and therefore arguably predicted. So all of these data challenges need to be attended to. The next slide talks about the market. This is a slide taken from the Ocean Enterprise study produced 5 years ago by the IU's program office. I know for a fact that my good friend Carl Goldman from the IU's program office will be talking to you about the update of this. But the important point to realize is that analyses have been done of what the revenue is associated with ocean observations. And if you look at the upper right, the revenue projections back in 2016 specifically talked about $7 billion US of ocean enterprise revenue. You're going to see some changes to all of these numbers. The point here is a lot of good work by a lot of very talented economists has gone into analyzing what the market potential is here. And we could talk at some length about that as well. Wait till you hear from Carl, you'll get a little bit more information on that. The other thing we need, next slide, is the workforce. And I'm really excited about some of the developments that we're seeing right now. There's some programs like Northwest Michigan College, which does an articulated associate degree, bachelor's degree program. There's a certification and credentialing program for chartered marine scientists that is currently being developed by the Marine Technology Society and the Society for Underwater Technologists with the Institute for Marine Engineering, Science, and Technology. And then I want to make a specific focus on, and apologize for all of the acronyms, so I'll read it out to you. The workforce development under the UN Decade of Ocean Science for Sustainable Development is focusing specifically on early career ocean professionals, ECOPs, and the Youth Advisory Council. And if I could have the next slide, there's a good reason for doing this. First keystroke, please. If you looked at our ocean community some 50 odd years ago, it basically looked like this. The Stratton Commission was the presidentially designated commission led by or overseen by Vice President Hubert Humphrey, shown here. And it's not a particularly diverse group. Some 20 years ago, next keystroke, please, we had the U.S. Commission on Ocean Policy. Delighted that 2 women joined the group, but still a bit of a challenge. And the final slide is a photo taken of that Youth Advisory Council for the U.S. National Committee. This is what our community needs to look like. This is how we need to operate in the future. And I'm delighted that the decade is focusing on these issues of diversity and inclusion. Next slide. The other thing we obviously have to have is capital. And if you can give me the next keystroke and the next one after that, one of my good friends, he's passed away quite a few years ago, is Neil Austin. So he was the head of NOAA Research for years, and he had a great saying. He said, you can lead with a stick, next keystroke, you can lead with a carrot, and final keystroke, but you can't lead with a tin cup. And the point here simply is we have to define what the benefit, the return on investment is, the yield associated with the new blue economy. We can't simply say, we think it's a good idea, please give us some money for this. I think with panels like the one here at the DC Forum, with continued discussion of this, this is going to be a really very much a leading with a carrot, if you will. I would point out that just recently, I was delighted to see the National Science Foundation put out its request for letters of intent on their Blue Economy Convergence Accelerator. This is an extraordinary investment by NSF, phase 1 awards of $750,000, basically to build out what I would argue are critical components of the new blue economy. So that coming from NSF is a really good example of public sector capital investment. And of course, there is philanthropy and private sector investment as well. The last element that we need for building out the new blue economies in the next slide, and it's policies. And I've called out just a few recent examples. There have been even more recently with the Biden administration, and it's everything from legislation to executive orders, international agreements, and of course, international programs like the UN Decade. Policies alone don't make these things happen, but they can be and often are a necessary but not sufficient element of building out the blue economy. Important to point out that all of these policies must include 2 important overlays. First keystroke is sustainability again, and the second keystroke is social justice, which has become increasingly important. The new blue economy cannot simply be a first world wealthy nation's economic sector. It has to be built on the needs and requirements of the global community. So as I close out, let me just give you a sense of what I think the vision will look like. Next keystroke. And the vision in a very tangible fashion is something like this. Basically, the ability to determine what are the futures going to be in fisheries? How might I invest in ocean catastrophe bonds? Cat bonds are a thing, but ocean catastrophe bonds is a very specific component. It's hard to read, but that third button says ocean energy products. Where do we cite wave energy, tidal energy? How do we determine the op tempo of these kinds of systems? Ocean forecast derivatives, we could go on and on and on. Health derivatives, for example. NOAA has some harmful algal bloom forecast systems. What derivatives might be developed from that by the private sector to develop a market? And then natural infrastructure management. A lot of discussion these days about building in oyster texture to protect harbors and ports from severe storms, or mangrove management. The whole point here is, can we be in a place where there actually is a market for investment? In closing, next slide, please. Vinod Khosla had this great quote some 6 years ago now. In the next 10 years, data science and software will do more for medicine than all of the biological sciences together. Pretty prescient, I think. Next keystroke, I'm going to commit the crime of plagiarism. And final keystroke, I will say, in the next 10 years, data science and software will do more for the blue economy than all of the ocean sciences together. Final slide, in a blatant and shameless self-promotion, please. Next slide. I wanted to point out that many of the ideas that I've shared here are actually coming out in a book where we've had some 50 contributors. My co-editor, Liesl Hotelling, and I worked with Elsevier to put many of these ideas together. Everything from the definition of the blue economy, to the economics of it, to the programs of practice, to the training requirements and workforce development. It should be coming out within just a few weeks. And with that final slide, let me just say thank you once again to the American Meteorological Society for the opportunity to participate and share some of my views on the new blue economy as a tee-up for what I know will be a wonderful panel. So thank you again. I'll turn it back over to Pam to take us through the next steps, or Ralph. I'm not sure who's taking it here.
Great, thanks very much, Dr. Spinrad. That was just excellent. So while I see some questions are already coming in, I'd like to let everybody know that although we're scheduled to take a break starting in about 2 minutes, it would be a 15-minute break. What we're going to do is we're going to actually keep the line open so that we can have plenty of time for questions. So we actually have a little over 15 minutes for questions before we go into our session. If you want to take a break, that's fine, but the rest of us will stay on and give plenty of time to hear more from Dr. Spinrad. So let me see. Let me read some of these questions here. So the first one here is this is a question from Dr. Adria Schwarber at FYI Science Policy News, which is with the press. Dr. Spinrad, do you think the time is right to revisit the idea of creating a national climate service? Secondly, if there is time to respond, how do you envision NOAA's Earth Prediction Innovation Center functioning at the agency in conjunction with Raytheon, which was just awarded the contract to develop the plan?
So I assume we have about 2 hours for me to address those questions. Let me try to be succinct, because those are really important and cogent questions. On the first one, I would characterize it as saying we need two things. First, we need a set of climate services, plural, and how we do it, I think, is a secondary issue. And I would add, those climate services need to be authoritative. So there are many different organizations and federal agencies that are putting out a variety of different climate services. How does the public, how do those intermediaries know which are the authoritative ones, which are the ones that are reliable? And so in many regards, in much the same way as the National Ocean Service and National Weather Service are established as authoritative sources for products and services, we need to make sure we do the same thing with respect to climate products and services. And we need to define well what those products and services will be. How we set it up, whether it's a capital N National Climate Service or a distributed function that's well understood by the users, is a question we're going to have to work on. But I would hate to see the focus on the how overwhelm the focus on the what. With respect to EPIC, the question of how do I envision EPIC functioning in conjunction with Raytheon, which was just awarded the contract. I have to say that I do not have deep understanding of what the nature of the contract is, but based on my own reading on the EPIC solicitation that went out and my own understanding of what needs to be done, Raytheon, the contractor, will be working to establish the ability to develop improved Earth prediction products and services. And I guess my point here would be that I, as so many of you do, hold deep, deep hope that it really is about an Earth prediction, which means the full Earth system predictive capability. And I would hope that what Raytheon does is serve as a facilitator for engagement by the full community. The concept of EPIC was that it would be a community-driven activity. And I am hopeful that EPIC does serve, that Raytheon does serve that function well. Thank you.
Okay, thanks, Rick. Okay, now we have a question from Renee Leduc at Narayan Strategies. Renee says, thanks for these great examples. A good chunk of the data to inform these information services relies on data relay from the NOAA GOES satellites. But this data relay is threatened by interference in the RF spectrum due to actions by the FCC to share this spectrum. So she says she would add spectrum to the list of concerns we need to address. Do you have comments on that?
Yeah, well, first of all, hi, Renee. Thanks for that question. Yeah, I think you're spot on. And I would argue that from what I've seen about the spectrum debate, first of all, I've got to believe in this day and age, we can resolve a spectrum allocation debate. And I think a lot of it boils down to marketability and economic prospects. And that the GOES satellite downlink spectrum requirements, what we should be doing is making very clear what the value, both in terms of safety and economic development for the American public is of having those products and services. The more we can emphasize that, the more I think people will say, yeah, we really do need to make sure that that frequency allocation is not compromised by other uses of the frequency.
Okay, next question from Dr. Julie Pullen. And she says, Rick, tremendously exciting presentation and congratulations on the book. She says, I am part of a group called Investable Oceans, and we engage with a number of women-led regenerative aquaculture companies and natural capital blue carbon solutions initiatives. Curious about your thoughts on these arenas and how we can continue to grow them.
Well, again, hi, Julie, and I'm not surprised about your question. I will be the first to tell you that as I go around giving a presentation like this or others, I'm hearing a lot about some of these very exciting emerging capabilities. I am committed to trying to make sure we have the dialogue, we have the communications mechanisms to understand who's doing what. I had a slide in this presentation, just didn't have the time to include it, that basically said who does what. And my intent was to list all of the various players. So from NGOs to the private sector to philanthropy to federal agencies, all of the above. I'm kind of punting a little bit, Julie, because it's not clear to me yet what the strengths of each of these groups might be. And if we can agree on what the expected outcome is, we need to have the dialogue. And I hope I am in a position in the not too distant future to bring these players to the table and talk about what do you think your stake in the game is. But the short answer is absolutely the organizations like Investable Oceans have got to be part of this dialogue. And I think the fact that you're already working on some of these issues, the aquaculture issues and the natural capital and blue carbon issues, is testimony to the fact that we need to get this right from the start. One small sort of op-ed perspective is, I know there was some of these kinds of discussions, say 50 years ago, between the emerging commercial weather industry and the public sector. Let's take advantage of what has happened over the last 50 years in commercial weather and make sure we're engaging the right players to do the right thing now for the new blue economy.
Okay, next question is from Dr. Rick Rosen. And Rick asks, how can the new blue economy contend with the degradation of the ocean environment, like acidification, warming waters, effect on fisheries, and plastic ingestion by fish and so forth?
So this is like old home week. Hi, Rick. I hope you're doing well. I would argue, Rick, that's exactly why the new blue economy is so, the concept of it is so timely and important right now. Let's just take one example that you alluded to, acidification. As you know well, Rick, because a lot of it happened when you were the head of NOAA research, the discovery of ocean acidification is less than 2 decades old. And the recognition now of how it will proceed, where it will proceed, and at what pace is in dire need of improved forecast capabilities. We're pretty good at it, but we really need to have better predictive capabilities, and then also predictive capabilities on what the dynamics are for ocean acidification. So I would argue, you phrased this as how does the new blue economy contend with these issues? And I would have said, how does the new blue economy facilitate addressing these issues even better? Now, the important thing, as you know well, Rick, is that it's one thing to take a highly skillful model and say we can predict or project impacts of temperature changes on fisheries or ocean acidification. It's another thing for policymakers to say, okay, therefore, we need to do this, this, and this. The CFC reductions to address the ozone hole is a classic example of where the scientists got it right, and then the policymakers had to make specific decisions about what to do and how to do it. So I would argue that the new blue economy is the critical first element to help the policymakers decide what do we need to do about emissions, what do we need to do about fisheries policy.
Okay, thanks. We're getting several different comments here. Excellent speech. I think you can probably read these. Let me go down here to another question from Eileen Shea. Probably also somebody you know. And she says, hi, Rick, and thanks for another exciting presentation. Would love to have your thoughts on the feedback loop from users to providers in your value chain in the context of shared learning. No surprise it's coming from her.
Yeah, no surprise at all, Eileen. How are you? So I think the short answer is the market is the feedback loop in most cases. If people are not buying your product, that's a pretty good indication from the users. But I don't think that's enough. And especially as we're building this out, there have to be mechanisms for the user community to feedback what they want, how they want it. Just as a short sidebar, I use the Portland grain shipping example because this actually happened when I was the VP for research at Oregon State University, where we had a faculty member who was producing a surface dynamics model for the lower Columbia River. She was doing this under a government grant for basic research purposes and putting her research results out on a website, publicly accessible website. When the grant finished and she shut the website down, my phone started ringing off the hook because the Columbia River port pilots had discovered this product and were using it to determine how to help the ships get in and out of the Columbia River. So you talk about customer feedback. That was a case in point, but there has to be some formalization in that. And I think that's another element of the discussion is how do we build that in there? But again, the short answer is that the market itself will serve as a feedback mechanism.
Okay, we also have a comment and a question, I think, from Sean Miller of Raytheon. And Sean says, Rick, completely agree with your comments on EPIC as a full Earth endeavor. The UFS application suite includes marine and coastal modeling. We definitely should talk about how to maintain priority across all of these different domains of modeling and the coupling between them. Did you want to address that?
I agree. Yay, verily. I think, I don't know if Louis is on the line, Louis Uchillini, but you know, he lives with this issue, as does Nicole LeBoeuf, as does the Fisheries Service, and many other federal agencies. Actually, Craig McLean once described NOAA as a $10 billion agency in a $5 billion box. And the point is, there are $10 billion worth of requirements. The agency could easily produce $10 billion worth of products and services. So how does one prioritize those requirements? Certainly, the head of the Weather Service has to go through that exercise, and we're going to have to do that. I would also add that this is where the dialogue between the private sector and the public sector becomes critical. It's one thing for a federal agency like NOAA to say products A, B, and C are priority. It's another thing if the private sector says, yeah, well, B and C are priority, but we really think D is a higher priority than A. Let's have that discussion. I would also add the potential outcome of that discussion is that an agency like NOAA comes back and says, we really need the resources to do A, B, C, and D, and here's the justification for it. Many of you have seen this happen with respect to severe storms of late. The investment, the damage from one Cat 4 hurricane making landfall far exceeds the investment in research and hurricane forecasting and prediction. And so consequently, one needs to make that sort of return on investment argument, and that's where the public-private relationship is critical.
Okay, great. Let's see. So just wanted to note that Louis Uchillini is on the line, of course, and
hi, Louis.
We were going to try to put him on audio, but let me read his comment. He just says, doing a great job explaining this opportunity, and there are many opportunities offered by a fully coupled Earth system model approach to advancing predictive capability.
Yeah, I love that Louis called out the fully coupled Earth system. I strongly believe that as an oceanographer who started my career by being told you have to select physical, chemical, biological, or geological oceanography, and refusing to accept that argument and transcending those disciplines, I have been a firm believer in the Earth system approach. And so talking about, for example, a wet NOAA and a dry NOAA has never made any sense to me. And so Louis invoking the Earth system approach is synonymous, in my view, with thinking about the interactions, the atmosphere, ocean, cryosphere, hydrosphere interactions are all part of that Earth system prediction capability.
Okay, I think actually, Louis, if you unmute, you're able to comment.
Okay, can you hear me?
Yes.
Yes.
So thanks, Rick, for the wonderful presentation and the broad view. You know, not only in the United States, but learning by being the permanent rep, you know, at the WMO, that this connectivity within the entire Earth system and include chemistry and biology and you know, is really being is now the driver for advancing our predictive skills across the whole system. And just to let you know that I do have Craig McLean's bumper sticker in my office. I left it there, you know, before we went into this mode. That if you love your 7-day forecast, thank an oceanographer. So, true believer.
Yeah, thanks, Louis. Appreciate it.
And it's great seeing you again. The last time we interacted, you had plantar fasciitis. Now you've got your shoulder. You know, take care of yourself.
I'm rebuilding myself piece by piece on the hopes and expectation that I can come back to DC as a whole man.
Oh, great seeing you again.
You too, Louis. Thank you.
Okay, thanks. So, so we've only got about a minute before we start our new Blue Economy panelist session. We'll give about a minute for maybe anybody who went off to a break to come back. But Rick, I just did want to, you know, my own question, something for you to think about, and I'd like to touch base with you on again about is this new committee that we have within the AMS that both Ralph and I are a part of. You know, we're going to have opportunities to help facilitate dialogue related to the blue economy. Within AMS, we can do that at sessions, at this meeting, every year, at the summer community meeting, at the annual meeting. but there are potentially other things we could do, white papers and so on and so forth. So I'm eager to help, and you know, we've got a great team on that committee, and I think look forward to any recommendations or suggestions you may have going forward on things that we could do.
Outreach. That's my one quick response,
Sure.
Pam. And I love that AMS is doing this. I know and respect so many of the people, you and Ralph, especially involved in this. I think if we keep this within the umbrella of the METOC, meteorological and oceanographic community, we will not succeed. So we need to bring in the economists. We need to bring in the public interest groups. We need to bring in the future developers. And I'd love to have that discussion with you downstream. I think it's critical.
Okay, great. Thanks very much. So we do have some other questions. We may come back to them at the end, but I think we're, you know, in the interest of time, we're going to switch over to our panel session. And Rick, you're able to stay on the line as well. So, you know, if you want to come in or come at the end of that with questions, that would be great. So now I'm going to go ahead and introduce our moderator for the panel session, my colleague in the new Blue Economy Committee, Dr. Ralph Rayner. Ralph?
Thank you, Pam, and welcome everyone to the new Blue Economy panel discussion. We're going to start with a presentation continuing the story of the new blue economy and providing some results of the latest ocean enterprise study that Rick mentioned in his keynote. Following that presentation, the rest of our panelists will then focus on one particular aspect of the beneficial use of meteorological and oceanographic information. Our focus will be on the value chain supporting the exploitation of offshore wind. Each of our panelists will give a short introduction to their perspective, and we'll follow those short introductory talks with a panel discussion and audience Q&A. To get us started, I'm pleased to introduce Carl Goldman, the Director of the NOAA Integrated Ocean Observing System Program Office. Carl is going to introduce the ocean observation value chain and the work that IOS has been doing to better understand the role of US businesses in the provision of new blue economy products and services. Over to you, Carl.
Thank you, Ralph. And thank you, Dr. Spinrad, for getting us going with an excellent overview of the new blue economy. Next slide, please. Next slide. So we've heard some of this from Rick's presentation before, but I'm going to get into a little bit more detail. Let's dive into the value chain connecting ocean observations and measurements to the delivery of end user safety, operational, and regulatory benefits, and supporting the sustainable use of ocean and ocean resources. We begin with the upper right with the observations and measurements themselves. They are made possible by many different sensors, instruments, and platforms, almost all of which are provided by specialist commercial businesses. Next comes the conversion of large quantities of data into usable information through data synthesis and modeling. Much of this is coordinated and undertaken by public organizations operating at a global, regional, national, and local scale. Organizations like IOS quality control and integrate data, assimilate data into models, and deliver spatial and temporal information about past, present, and future states of the ocean, coast, and Great Lakes. The resulting core ocean information is made available via portals, the public good, and public and private intermediary organizations access this core information to enable the creation of value-added information products, delivering benefits to particular end users. These intermediaries add value through further analysis, blending with other data, and sometimes end-use specific modeling. Finally, at the end of the chain, end users derive specific benefits from information tailored to their specific needs. Of course, the chain does not end there. It is vital that knowledge of the present and future ocean information needs of intermediaries and end users are fed back into the value chain, creating a virtuous circle where the future design of observing system and selection and development of the technologies that support it evolves to meet emerging needs and the availability of new technologies. NOAA is conducting work to better understand each of these components of the ocean observing value chain. Next slide. As part of the Department of Commerce, NOAA's mission includes facilitating and supporting US business activity. And private businesses play a key role in the value chain, as I mentioned, as providers of the technology comprising the ocean observing system, as intermediaries who create the tailored ocean information products and services, as an important segment to the end users who derive benefit from the use of ocean, coastal, and Great Lakes information. For NOAA and IUCE, private industry has developed and supplied much of the technology in our observing networks. Examples include the sensors and platforms you saw earlier, and others such as our high-frequency radar network, our marine biodiversity observation network, our animal telemetry network, and the buoys and underwater gliders we use. Next slide. The vast quantities of data collected by the many elements of the ocean observing system must be converted into useful information in order that they can be used to support their application. This is a key activity in IUCE, converting data into information through quality control, analysis, and use in models, and then making this core information available and accessible for public and private use. The IUCE data management and cyber infrastructure subsystem makes possible the discovery, understanding, and access to ocean, coastal, and Great Lakes information through data portals in each of the IUCE regions and through national service delivery portals as well. Next slide. Public and private intermediaries use this core publicly available ocean information, often in conjunction with other types of public-private data and information to create and deliver specific information products, providing benefits to the blue economy end users. Next slide. The end users derive safety, operational, regulatory compliance, and environmental protection benefits from a huge range of value-added information products, which have been specifically tailored to meet their needs by public and private intermediaries. The range of end users of ocean information across the blue economy is incredibly diverse, with each segment of the blue economy having its own unique requirements. And as the blue economy develops, new requirements are constantly arising, and with the constantly evolving ecosystem of public and private organizations rising to the challenge of serving these developing needs. Delivering the ocean information needs of the designers, installers, operators, and regulators of offshore wind power systems offers a great example of the need for new information products now and into the future. Supporting wind turbine installations in shallow water has created many new ocean information needs. A move towards large-scale use of floating wind installations will create many more. Next slide. In order to better understand the ocean observing value chain, NOAA and NOAA IUCE conducts a wide variety of economic studies. These help NOAA to deliver its mission and its commitment to supporting the sustainable use of ocean and ocean resources. These studies also help NOAA to understand how best to interact with and support business activity across the value chain. Next slide. So the ocean enterprise studies we've conducted, 2 of them now, are a key component of this work. First one was done in 2015 and then repeated in 2020. They aim to provide a detailed understanding of the scale and scope of US business activity in the provision of ocean observing and measurement technology and the activities of US businesses acting as intermediaries, creating value-added information delivered to end users in support of their activities on, in, and around the ocean. Through repeat studies, NOAA and IUCE aims to provide an understanding of how these important activities, Rick Spinred's new blue economy, are developing over time and responding to the changing and growing information needs of end users comprising the overall blue economy. The 2015 study report is available for download on the NOAA IUCE website, and currently analysis of our 2020 study is underway and almost complete, and the study report will soon be published, at least by June is our projection. And time precludes me giving you a detailed review of the studies, but I will draw a few key findings. Next slide. You got the 2015 results on the left and 2020 on the right. This is a summary slide with a map of where the companies are located. In the 2015 enterprise study, we identified over 400 businesses active as providers of ocean observation and measurement technologies, or who acted as intermediaries, creating and delivering ocean information products, supporting the needs of end users. Collectively, these businesses generated, as Rick said earlier, $7 billion in revenue, and over $1 billion was exports of these goods and services around the world. And then in 2020, the number of businesses has exploded to nearly 900, generating over $8 billion in revenues, with around twice as much in export activity as there was in 2015. Next slide. This is a bit of a small chart. The left side blue bars are 2015 results, and 2020 results are in orange. And what this is showing you, it gives you an idea of the size and experience of responding firms and how that's changed over the last 5 years. So on the left side, you have number of locations, and the number of firms trading from a single location has grown by over 20%, and the number of firms with less than 3 years experience in ocean enterprise activities has more than doubled. This is consistent with there having been a large number of new startup companies created in the period since the 2015 survey. And at the other end of the scale, the survey has identified a great deal of consolidation, with many of the businesses in the 2015 survey having been rolled up into larger businesses through mergers and acquisitions. Next slide. In this graphic, we see the proportion of firms that are intermediaries and providers or both in 2015 and 2020, and this distribution has remained remarkably consistent. Total employment numbers on the right shows that respondent firms also had growth in the small startup businesses over the period and growth of larger businesses and a reduction in the number of the mid-sized firms. And that's due to the mergers and acquisitions as I described earlier. Next slide. Activity across the customer sectors has changed in several important respects, and I've highlighted a few of them with the blue, light blue boxes here, reflecting changing market opportunities as across the blue economy. Of particular relevance to today's panel is the growth in activity related to ocean renewable energy. Numbers of firms engaged in renewable energy market, mostly offshore wind, has almost doubled. Since the level of end user activity in the offshore wind market in the US is currently small, this indicates that US businesses are very active in exporting their technologies and services in support of the needs of offshore wind, especially in the currently much larger European market for these. Other areas of significant change are the growth in activity in meeting water and water quality monitoring needs and supporting coastal protection. In the chart on the right, you can see the types of technology products being provided. Not surprisingly, the number of firms involved with the provision of measurement platforms has grown substantially, reflecting the massive increase in activity in provision of autonomous vehicles as platforms for ocean observation since 2015. The full report of the 2020 study will dive into much more detail than I have been able to cover in this short presentation, and look for it around the June timeframe, as I said. And then as other nations begin to evaluate the ocean enterprise, next slide, sorry. As other nations begin to evaluate their ocean enterprise businesses, we can start to build up a picture of the global new blue economy activity. Based on their other studies and economic analysis, overall business activity in the provision of technologies in support of ocean observation and measurement and ocean information products is estimated at around 25 billion per year. And as I mentioned before, look for the full report, which will come out on our Ocean Enterprise Study 2020 near June. Next slide, please. In the final few minutes of my presentation, I would like to introduce you to an exciting new project aimed at better understanding that final part of the ocean observing value chain, that end users, which is one of the old pieces to study. What we want to do is understand the benefit users derive from using ocean information products to ensure they operate safely, effectively, and sustainably on, in, and around the ocean coasts and Great Lakes. Next slide. So we're building what we're calling the Benefits of Ocean Observations Catalog, or book for short. Currently, there are many use cases of widely differing levels of detail scattered across many organizations concerned with making ocean observation and measurements, or with deriving benefits from their operational use. The objective of the book project is to create and maintain a community repository for such use cases, bringing together qualitative and quantitative studies which demonstrate the societal and economic value of sustained ocean observation, measurement, and forecasting. It is hoped that with this will become a widely used community tool for demonstrating how public and private sector efforts come together to deliver important societal and economic benefits in many different ways in many different places. Next slide, please. So the book comprises 4 main components. We're going to have an interface to allow input of disparate data, use cases, different use cases into the database, capturing the key attributes of each, the ability to search that database either geographically or by end use application or by type of ocean information used, and then the ability to generate focused reports about a particular type of use or a particular ocean region or a particular class of observation or measurement. For example, to be able to compile a report of all the benefits of ocean observing information in support of offshore wind energy. As we start the work of building this capability, we invite you to learn more about the project and contribute any use cases you may have for inclusion. You can find out more about the project at www.booc.info. Next slide. I hope that my short presentation has given you some insights into the work that NOAA and IUCE are doing to better understand the value chain delivering societal and economic benefits from ocean observation and measurements, supporting NOAA's mission, to understand and predict changes in the climate, weather, water, oceans, and coasts, sharing this knowledge and information with others. What you see in this image is a presentation. Next click, please. And next click, please. A presentation by our Pacific Islands Regional Association Director, Melissa Iwamoto from OceanObs 19. She was describing the ongoing stakeholder engagement processes each of our regions use to try to understand how to meet the mission requirements in the center of that circle by understanding the specific user needs, providing information services related to those needs, and iterating with the customers on an ongoing basis to refine the service delivery of those products and services to ensure we're meeting the needs. And in many cases, this circle includes partnerships with both public and private sector entities in this ecosystem of players that I've described in this Ocean Enterprise discussion today. So with that, I'd like to thank you and pass it back to Ralph for the rest of the panel.
Thank you, Carl. We have got time for a few questions. I don't see any appearing in the chat yet. Does anyone have any questions that they would like to ask of Carl before we move on to the rest of the panel? Anyone on the panel have any questions of Carl? Looks like you might get off lightly here, Carl. Okay, so seeing no questions coming in, I'm going to move on to the short introductory talks from the rest of our panelists, and we're going to start with Ben Williams. Ben is the MetOcean Director for the Americas region at Fugro. Fugro being a multinational company specializing in geodata to support client projects on and offshore. Over to you, Ben.
Thank you very much, Ralph, and thank you to Carl and Rick for their excellent presentations. I'm going to focus on a niche component and some of the initial characterization and ocean observations to support renewable energy. Next slide. So wind is an offshore energy resource with 95 million people living in coastal counties. This represents approximately 30% of the US population. Offshore wind is ready for takeoff in the US. Offshore winds are typically stronger during the day, providing a stable energy supply when consumer demand needs it the most. Remote sensing technologies such as satellite-derived winds are great for understanding winds over wide areas and making site selection decisions. But to make investment decisions and project-specific wind resource assessment direct measurements at sites need to be conducted. Next slide. Traditionally, Met towers have been utilized to quantify wind resource data from wind farm developments. The ability to quantify bankable wind resource data is critical in both the funding and development of any wind farm project. Met towers provide very well understood data from CUP anemometers. This is not just for mean wind speed, but also for wind turbulence data. There are many challenges that exist, though, with the installation of offshore Met towers. The installation of a tower requires foundation design, installation, operation, and decommissioning. The process of permitting and operating these systems can be onerous and expensive. Towers are generally limited to 100-meter height, which in most cases reach the hub height for offshore wind facilities, but fail to characterize the full blade tip reach in new structures being brought to market these days. Understandably, Met towers are also impractical for floating wind as that becomes more prominent around the globe. Next slide, please. Wind LiDAR buoys have in many or even most cases replaced Met towers to support offshore wind developments around the world. At approximately a tenth of the costs, wind LiDAR buoys are able to quantify wind resource data and reduce project risk and reduce project development costs when compared to Met towers. The vast array of parameters that can be measured from a buoy-based system provide differentiating solution for Met towers. the ability to quantify the wind resource, as well as environmental forcing that would be exerted on the wind farm after installation, allows for improved engineering and reduction of construction costs. The buoy's ability to carry a suite of environmental sensors further reduces development risk by giving understanding to the impact the wind farm development may have on its surrounding environment. Specifically, Fugro's Sea-Watch LiDAR buoy provides all the benefits from the previous slide, but I can speak more specifically about the capabilities. Our buoy has been in development and production since 2010. We were successful in reaching the pre-commercial stage by 2015. It's important to note that the pre-commercial classification from the Carbon Trust does not stop buoys from being utilized commercially, but it requires them to perform pre-deployment validation ahead of installation on site. Fugro's buoys measure wind profiles up to 300 meters above sea level, but are only validated at 250 meters height. This validated height covers the blade tip reach of most modern wind turbines. As a Sea-Watch system has been built upon a well-proven buoy hull, there's no compromise made in the quality of wave data collected, as it's understood to be a critical development parameter, and full directional wave spectra is collected from all of our systems. Current profiles are typically measured in the up to 80 meter range, as this supports the majority of wind farm developments on continental shelves these days. But the Sea-Watch system does support much longer profiling instrumentation up to 800 meters range on installations around the world. So I can touch on what the future holds for Fugro's LiDAR buoy. We're currently completing the final required data collection campaign to support the Carbon Trust Stage 3 commercial classification. I think we're 3.5 weeks out on completing that study, at which point we move into the third-party audit and review of the data we've collected to meet the criteria for this Stage 3. We hope to reach that by Q4 of this year. I can touch on turbulence as a key parameter for offshore wind farm design. LiDAR buoys do an extremely good job of quantifying the mean wind velocity, but due to the buoy motion, tend to overestimate turbulence intensity. We're continuing to develop our processing and analytics for turbulence. Through post-processing, we've made advances in motion compensation, and in offshore trials have been able to bring the results in line with fixed LiDAR systems. We have published some of the findings of these trials in the paper I've referenced here above, and there's a graphic of the blue line showing unmotion corrected and the red line showing the corrected plots. Now we move on to some interesting part, and we actually have some data presentations here. So we're able to share this data because we've collaborated with our clients, in this case Mayflower and Atlantic Shores, to make available a large portion of the real-time data through the IUS regional associations. This allows for public access to the data, and we know it's being used by university students and researchers, and we hope it's being used by fishing communities operating in these areas as well. The Mayflower data is available via the Nirakus site displayed here, although I checked about an hour before my presentation, and we just completed the service visit this week, and I'm hoping the data feeds back up this afternoon, but nothing like timing, right? The Mayflower data here is from Tropical Storm Isaias that made its way up the eastern seaboard during the extremely active 2020 hurricane season. Isaias's track is shown in the black line, and the Mayflower buoy location positioned south of Massachusetts. In the 30 meters of water depth at the buoy location, we experienced maximum wave heights of 6 meters and wind speeds in the profile in excess of 50 knots. Next slide. And moving further south to the other location that was presented in offshore in New Jersey, the Atlantic Shores buoy system makes its data available via the Maracus site. I provided the address for the Maracus data portal here. The Atlantic Shores buoy was much closer to the eye of Isaias, where wind speeds were seen in excess of 75 knots from the profile. Wind-driven currents were seen reaching the seabed with a maximum speed of 2 knots, and as expected, the air pressure falling to nearly 1,000 millibars. This data from both sides will be used to develop important criteria when the operators design their wind farms to operate and provide energy for the coming decades. So with that, I'd like to thank my fellow panelists and
thanks very much, Ben. And that's a great introduction to some of the novel technology being developed specifically to support offshore wind. And I would mention also, Ben talked about the Carbon Trust, and that's an organization based in the UK that's played a very interesting role in facilitating joint industry projects to develop and support the technologies needed in the offshore wind sector and amongst other renewable energy sectors. So I'm going to move on to our next panelist, Sue Ellen Haupt. Sue is a senior scientist and deputy director of the Research Applications Lab at NCAR. Over to you, Sue.
Thank you, Ralph. I'm pleased to represent the research community on this panel, talking about the way that we can fill in that part of the value chain between where we measure the data and where we actually have intermediaries providing information. How do we build the models using the data, and what are the next generation models going to look like? In addition to representing NCAR, which is sponsored by the National Science Foundation, I'm also going to be talking about work done in partnership with DOE's Wind Energy Technology Office, especially 3 additional labs, NREL, PNNL, and Lawrence Livermore National Lab. In the next slide, I show the focus for some of the DOE technology development for these offshore wind. The challenges are that we need high fidelity models and design tools so that we can plan better for these offshore wind turbines. So we can look at the interactions between the ocean and the atmosphere. We need to scale in better ways. And especially when we talk about looking toward floating offshore wind, we need to be able to couple the atmospheric ocean models with the turbines and the foundations. And there's going to be uses like trying to control to get more power from these wind turbines. So that implies that the modeling needs for the coupled models are going to be not only the mesoscale models that we're so familiar with, but also microscale models where we can embed turbine interactions, the interactions with the ocean, the sea surface temperature, but also the waves and the turbines themselves. Next slide, please. And in particular, there's some meteorological phenomena that we know are important, particularly in the offshore environment, that are not well modeled yet, that we can do better jobs and provide better information for the downstream users. Things that happen both onshore and offshore are things like low-level jets, just the diurnal cycle, the changes from the stable boundary layer at night to the convective boundary layer during the day. And a lot of the standards are made for neutral conditions, which may not actually occur very often. Frontal passages are very important, as well as the waking of wind farms on the downstream wind farms. But then some of the specific things for the offshore environment include land breezes, sea breezes, when we have cold air outbreaks over a warm ocean that causes interesting types of convection, the fine scale ocean discontinuities that cause a discontinuity with SST that drives pressure differences, wind wave coupling, impact of precipitation on turbines, and as mentioned previously, tropical cyclones. So the next slide reiterates the point about data being very important, but very difficult in the ocean environment. There's very few towers that have been out over the long term that help characterize the resource and provide the data information that we need for the data, the big data uses like machine learning. Thus, as we just heard from Ben, having LiDAR buoys is very helpful. And in fact, DOE has been deploying LiDAR buoys. So they're able to measure the wind profiles, the near surface met-ocean conditions, things like wave height, period, directional spectrum. And that type of information is critical for developing these wind farms. Now, the next slide really indicates how important this wave atmosphere interaction can be. We see here some work by Peter Sullivan that demonstrates how the waves themselves cause pressure differences in the atmosphere. And those pressure differences cause wind variability that persists up to hub height and beyond. And it depends on the relative speed of the waves themselves as well as the wind, and whether that characterizes the waves as old waves or new waves. Now, a further impact is shown in the next slide, where we look at another important wave atmosphere interaction is the direction of propagation of the waves. And the large eddy simulations can really demonstrate that. In the top plot, you see that when the winds and the waves are propagating in the same direction, we get higher wind speeds than in the bottom plot where they're propagating in opposite directions. In that case, the directional difference provides more friction and lower wind speeds. Understanding these sorts of things really helps us decide how better to design, deploy, and operate the wind plants. So the next slide talks about some work that we've been doing as part of this ocean atmosphere wind coupling project that I oversee between these various labs. We've been looking at cases. We've been downscaling from the mesoscale to the microscale model using real data. And our first case study that we've been working on for a little over a year now actually goes to Europe. And that's because there are 3 longstanding towers off of Europe, the Pheno towers, with a co-located wind farm, the Alpha Ventus wind farm. And we've gone back to 2010, where we had turbulence data and modeled a 2-week period. Now, the mesoscale models themselves require modification to provide the high resolution simulations we wish in the offshore environment. You know, for instance, we added an algorithm for offshore surface roughness that includes the effect of changes in bathymetry. We ran a 2-week period of the mesoscale, coupled the microscale. We're planning on doing turbine simulations. And you know, this is providing us information to better understand the coupling for better modeling. We're also using machine learning to build new surface layers so we can get better fluxes. And we've already started a Northeast case using some of the same LiDAR data that Ben has just talked about. So the next slide just gives you a flavor for the type of mesoscale simulations that we've done, where we vary things like the planetary boundary layer scheme that we use, the sea surface roughness, the way that we model it, the sea surface temperature, how we bring in the data. And we're able to compare these different methods and look at them in terms of performance diagrams so that we can find best ways to model. The next slide shows how we've then coupled to the microscale models. The top plots are a series of plots showing differences when they're embedded in the weather research and forecasting model, where the left ones look at providing cell perturbations in WRF so that we develop a mixed layer more rapidly at the microscale than we would be able to do otherwise. But on the two plots on the right also show that synthetic perturbations, such as the Mann method, can also induce turbulence. Now, a lot of the turbine element blade models are employed in standalone LES models like SOFA, developed by NREL. And they're looking at coupling using tendency perturbations, using data assimilation in a similar way that we do for our weather modeling, but in this case to force the microscale modeling. And we find that we are able to get those microscale models following the mesoscale models. Now, the next slide looks at the downstream. How do once we have the turbulence generated from a wind turbine, how does it impact the one behind? And can we actually control the direction of the upstream turbine so that we can harvest more power from the downstream turbines? And you can see in the simulations at the bottom, the left is with no steering, the one on the right is with steering, and you can see the with steering line is the green curves in the plots just to the right of that, and that we can get much better power production if we have models that tell us how to steer the wind. So the final slide, I'd like to summarize some of my points, that we're doing lots of research, we're building better models that will allow more accurate resource assessment, as well as providing design tools that actually couple with the turbines and build better turbines, as well as better ways to deploy them. That will allow more efficient operation in real time. Although the measurements are sparse, the data methods are becoming better. We're finding that the IEC standards could be improved beyond just the assuming neutral conditions. And we are learning to better model the atmospheric phenomena, the full interaction with the waves and the ocean, and providing tools that can be used for the downstream people to better deploy wind energy for the blue economy. So thank you.
Thank you, Sue. You've given us an excellent insight into the whole issue of taking some of our tools and techniques and bending them to the specific needs of a particular application. Our next speaker is Mark Calverley. Mark Calverley is co-chair of the IMRS Offshore Renewable Energy Special Interest Group and works in providing value-added information products in support of offshore wind developments in Europe and Southeast Asia. Mark, over to you for your presentation.
Sorry, good afternoon, and thank you very much for the invitation to speak at this conference. I am representing the IMRS today, and I will give you a little bit of background on them in case you're not familiar with them. So could you move to the next slide, please? IMRS is a global learned society that supports marine professionals through a number of activities, including training activities, such as its Met-Ocean Awareness course, peer-reviewed publications, such as the Journal of Operational Oceanography, and special interest groups that address specific needs in the marine environment, such as ocean governance, operational oceanography, and offshore renewables. The offshore renewables special interest groups facilitate sharing knowledge through workshops and webinars, such as the one you see on the left here, which is designed to bring together wind resource, which historically has been terrestrial knowledge, and Met-Ocean, which historically has had wet feet. So we're moving away from dry and wet, as suggested earlier by Rick. It also supports broader IMRS initiatives such as the Oceans of Knowledge Conference, which is a biannual event which seeks to connect researchers, data providers, value-added companies, and end users to better realize and also recognize the ocean observing value chain. This year, the Oceans of Knowledge event is looking at climate change and the ocean with a particular focus on the energy transition and how observation supports that transition. Next slide, please. With respect to the wind farm market, there are several drivers, and the first is the standard-driven data and information needs, and Sue alluded to IEC, and there are two main bodies of IEC standards, one addressing the atmosphere and turbines themselves, the second addressing metocean and the support structures and foundations supporting those turbines. The wind resource element is deeply rooted in the terrestrial wind processes, and some of the approaches do not readily translate to the marine environment. So the work that, research work that Sue Ellen presented is very welcome in this regard. I think the biggest challenge there will be expediting the knowledge to be put into the design codes in a good way, so that we can actually make use of that knowledge. The metocean component has drawn on oil and gas experience, but some anomalies remain. For example, typical extreme criteria for offshore winds are 50 years for a wind turbine, 500 years for an offshore substation, and this compares to 100-year and 10,000-year returns used in oil and gas, which is driven by safety of life and environmental issues. The approach to extreme value analysis isn't consistent between those two knowledge bases, or the two areas. And in the UK, I've certainly seen quite a lot of conservatism where value added, and I put value added perhaps in exclamation marks or in quotation marks, provide inappropriate metocean design by using generic contours of wind speed for various return periods that were developed by the HSC regulator and really aren't appropriate to offshore wind. The next slide, please. Beyond the standards, there's really three main elements that have to be addressed when developing a wind farm. The first is wind resource, so how you get the watts. The second is the metocean, and that drives design and operations. And the third is the environmental impact assessment component, where the physical oceanography is having an impact on seabeds and the ecosystem itself. The broad range of requirements is best addressed holistically in terms of data collection for both cost efficiency and consistency of data. However, this requires a broad knowledge of the needs of the different areas, or particularly good communications between the disciplines within companies and those specifying data collection. If the needs aren't addressed holistically, this can really provide challenges in terms of satisfying the regulator and also consistency in the design basis. Another important consideration in this is data management. It is important to ensure that the data are discoverable to those requiring value-added products and services, and also readily accessible with appropriate metadata. A learning point I would say from the UK's initiatives in this area, the regulator requires all data collected in support of offshore wind projects to be submitted with discovery metadata and made available via the Marine Data Exchange. There's two major drawbacks of this system. Firstly, the data are not available via an API, so programmatically you cannot access them, and the access is best described as archaic and rather time-consuming. The second one is that although discovery metadata are available, evaluation and application metadata are not required. This often leads to data that are not fully described with respect to how they were collected, the quality control that has been applied, and any analysis applied to them. And this can render them useless to the applications of further down the line. Next slide, please. Through the life of a project, different services and products are required, generally based on different data. Pre-license use of off-the-shelf data comprising historical measurements, often from ocean observing systems. And I was presenting to a Korean client this morning where very fortuitously I had 10 years of Korean goose data, 1 kilometer from a wind farm development. So not only could it be used in pre-license, but it could be used for the whole wind farm development. So coming from ocean observing systems, industry measurement, regional models, and also strategic environmental assessments. At this stage, the wind models may be downscaled, but without proper validation. These data at a broad scale are generally sufficient to understand the likely wind resource, potential engineering concepts, operational constraints, and that can be used to drive a financial model to support the license application. All these aspects add value to the ocean data. As the project moves forward, site-specific data is required, as mentioned by Ben, to reduce the uncertainty and optimize the design and operation. The data will comprise in situ measurement and local modeling, or microscale modeling potentially, with more detailed analysis services being applied to meet the requirements of the end users, such as the regulator, certifying authorities, and engineers. Next slide, please. The atmosphere may be considered the new hydrocarbon reservoir. Value adds in this area extend to wind resource assessment, to optimization of field layouts, metocean design basis, and operational criteria. Understanding the impact of the atmosphere on the wind turbine and support structure is critical to optimizing power production. It is somewhat challenging, and the image on the left is designed to illustrate some of the problems faced. The LiDAR systems presently available are certified to or verified to 200 meters. New turbines may have hub heights of 160 meters with rotors extending to nearly 300 meters. The present codification requires FLIDAR performance against met mass, which typically extend to only 100 meters. So only a small component of the wind profile is actually calibrated and verified. The offshore rotors are far larger than the onshore equivalent, so learning cannot be transferred in terms of behavior, etc. This is an area that offers significant value-add options, as presently operators often claim that turbines do not operate to their specification, and turbine manufacturers, operators claim that turbines do not operate to the specification, and turbine manufacturers claim that operators are not controlling the system properly. This is partly derived from the black box approach of the turbine manufacturers. The IEA Task 32 work group has begun to address this through consideration of digitalization of LiDAR measurements and has put forward user stories regarding wind farm control, forecasting for maintenance access, and power forecasting. I think the latter will be particularly interesting when we start looking at energy storage and the potential for green hydrogen being produced offshore, and whether you put your energy into the grid or whether you actually put the energy into storage for peak grid times. So this is an area where I expect to see significant value-added services in future. Next slide, please. The metocean requirements across the life cycle of a wind farm have been addressed in the American Clean Power Standards US Offshore Wind Metocean Condition Characterization Recommended Practice. This document is likely to be made available in Q4 of this year. It will shortly be out for review, and anyone can contribute to that review, I believe. It's probably the first guidance document that actually recognized the role of the marine technologists. When I was involved in the author of this, along with Ben and others, and it was quite astounding that the professional engineer who builds the turbine or designs the structure, the certifying authority were all clearly identified and their roles clearly laid out. The people actually providing all the data that supports their activities weren't recognized initially. So we made sure that the role of the marine technologist and the MTS program is in that document. This figure from the report illustrates the types of data commonly used, and the value-added services include metocean design bases, operational planning tools and management tools, understanding structural responses due to environmental forcing, driving novel methods for fatigue assessments and structural inspection, extending life extension through to understanding the metocean conditions experienced through the asset's lifetime and how they have changed. Has climate change actually changed the conditions such that repowering is not an option because the conditions have worsened potentially? Next slide, please. Oceans observations also inform a number of value services with respect to environmental impact assessment. And really this could be considered broader than environmental impact assessment and to the extended to users of the marine space. Metocean and seabed sediment data feed into metocean and coastal process assessment, including potential impacts on sediment pathways and their impact on the coastal morphology and ecosystem. Underwater sound is now recognized as a key environmental indicator. The sound characterization is very important, and the services that are provided to use the data to characterize ambient sound and the presence of marine mammals is critical to satisfy the regulator and also help plan mitigation for impulsive sounds generated through construction of wind farms. And the last slide. So the value-added products and services are multi-dimensional. There's a whole group of them here. When we think that the global offshore wind market could extend to 234 gigawatts of offshore wind in 2030, and we look at the growth in the value that Carl showed in his presentation, this suggests that the demand and value for these services will grow dramatically over the next 10 years. I think the growing market also offers significant opportunity for innovation of services to meet gaps in information and knowledge to optimize the design and performance of both wind turbines and structures. And that's it. Thank you.
Thank you, Mark. And thank you for providing a few really nice examples of how the requirements change with the changes in the technology being put into end use. This is not a static thing, it's a dynamic thing. We've seen wind turbines go from very small things to extremely large structures with some very challenging requirements. Now, I'm not sure whether our final panelist is actually still online. Well, she's back, yes, okay. So our final panelist presentation comes from Angel McCoy. Angel is a meteorologist in the Office of Renewable Energy Programs at the Bureau of Ocean Energy Management. Over to you, Angel.
Thank you very much, Ralph. And thank you for inviting me to be here today, Pam. And I look forward to sharing with you more about the Bureau of Ocean Energy Management and specifically our work in the Office of Renewable Energy Programs. Next slide, please. So first, BOEM, I'm going to call it BOEM for short. We get our regulatory authority from the Outer Continental Shelf Lands Act and the Energy Policy Act of 2005. And in short, we have the authority to expeditiously and orderly develop our national resources in the Outer Continental Shelf. And those sources include minerals and renewable energy. So other than oil and gas, as we're more commonly known for. Next slide, please. So the mission of the Bureau of Ocean Energy Management is to develop our nation's resources in an environmentally and economically responsible way, and to manage these resources for environmental sustainability, economic development, and national security. And we value stewardship, science-informed decision-making, integrity, and ethics. And much of this presentation will continue down the road of this science-informed decision-making. Next slide, please. Let's see. Well, I see that this isn't necessarily the presentation that I wanted, but we're going to go with it. So here is a map of the outer continental shelf. It's focused in on the Atlantic. And, don't get overwhelmed by what you see here on the screen. But here I show our current lease areas and then call areas and areas that we have identified. They're labeled as wind energy areas. They've been identified for being made available through competitive lease auction. I will bring your attention specifically to the inset offshore the Rhode Island and Massachusetts area. That blue area there that's labeled Vineyard Wind, that was our most recent lease sale in December of 2018. Well, that area in blue, we just published a final environmental impact statement on that area. We will soon issue a record of decision for that area, whether or not we've approved the project and how we're going to proceed. Then further to the east of it, those three lease areas that are labeled Equinor, Mayflower, and Vineyard Wind, the Liberty Wind project, those were a part of our most recent competitive auction process. Those three areas sold for a combined total of $405 million. Each lease area separately were sold for $135 million. Just to help put that in perspective, back in 2013, we had our first competitive lease sale, and for two areas, that totaled only 3.8 million. So in a short time frame, we see an exponential increase in the dollar value of these lease areas. Next slide, please. So here's a high-level overview of the authorization process for offshore wind, or I should say all renewable energy. And you can go ahead and tap the keyboard. There we go. So first, there's the planning and analysis phase. This takes about 2 years, and it involves the involvement of the Intergovernmental Task Force that's made up of state elected officials or regional elected officials. And it involves the involvement of tribal nations. In this time frame, we do the call for informations. Like I showed you on that previous slide, there were areas that were identified as call areas. When we do the call for information and nominations, what we're looking for is more information on the areas we have identified as potential wind energy areas. We're looking for interest in the development of those areas from developers, future lessees. In this time frame, we're also doing the area identification process. So that's when we're narrowing it down to a wind energy area to be made available for leasing. And we conduct environmental reviews. The environmental reviews only cover site assessment and site characterization. Next, please. Then we enter into the leasing process. That starts off with a proposed sale notice, followed by a final sale notice, the auction, and the actual issuance of leases. Next. Then enters the site assessment phase. So this is when a developer would submit to BOEM their site assessment plan in order to do the site characterization surveys and in order to install the metallurgical tower or buoys. As the presenters before me stated, everyone's doing metallurgical buoys these days that are more cost effective. And next. Then the last part of our process is the construction and operation phase. So after collecting this data over the course of at most 5 years, unless an extension is requested, The developer would then submit to BOEM the construction and operations plan or their project plan. After that has been received and reviewed by BOEM, we would conduct an environmental impact analysis. That is the more thorough examination of environmental impacts. Mark already touched on this, but the more thorough examination of environmental impact of a specific project. After that, we would approve the project or approve of modifications, or we would deny the project. We would issue a record of decision. And once all of that is done, the developer is then able to submit a facility design report and their fabrication and installation report. This is only for us to do that final check and to issue a non-objection that this is consistent with what was analyzed in the construction and operations plan. It's also an opportunity to double check for safety, for the design standards that are being implemented based upon the site-specific information that they've collected during the site assessment phase. Once a project is operational, it is expected to be operational for about 25 years, and then it would enter into decommissioning. Next slide. And so I mentioned in that larger image of the whole Atlantic, areas identified off of New York as call areas. Since then, we have narrowed this down to wind energy areas, to proposed wind energy areas, and they were presented to the Intergovernmental Task Force of New York. Was it last week or the week before last? I think the week before last, had a meeting to just to engage the task force. And we also had opportunities for the public and other stakeholders to engage with BOEM to talk about why the areas have been identified in the way that they have, whatever questions or concerns they may have. One thing you may all note is the spaces that are here between the fairways, North Fairways, South Hudson, North Hudson, South. Those are traffic separation areas as advised by the US Coast Guard. I also want to note that in these call areas, the whole area would not be automatically made available. In my updated slides, it shows where it was narrowed down just a bit more into smaller areas that deconflict some of the other stakeholder interests and usage of these call areas. And I also want to point out that it would not necessarily be one large Hudson South lease area, but smaller lease areas. We're looking to break that Hudson South up into smaller lease areas. Next, please. So these are some factors for consideration when identifying wind energy areas. As a meteorologist, I would love to say it was just the wind resource, but it's not. So we take a look at industry interest. We look at recreational and commercial fishing interests, impacts to the viewshed or potential impacts and ways to mitigate those to the viewshed, protected species. We collaborate with other federal agencies. We consult with the US Coast Guard so that we can work with them regarding navigation and maritime safety. We look at radar impacts. Next, please. And so now I want to take a moment to, I guess, reel us into more of the engineering and the technical aspects of this work. And that's where the atmospheric and oceanographic data come into play. We have a number of funding mechanisms. The most widely used would be our technology assessment program. And so this is where we are able to fund research and studies to better inform the development and the operational safety and environmental protection related to offshore energy development. We use the results of these studies in order to develop the standards, guidelines, and engineering practices. And this is done through broad agency announcements or the request for proposals. We also issue requests for quotations. Historically, we've done cooperating agreements, but we are getting away from that. We do have a few studies that were funded with universities and state agencies that way. And we also do interagency agreements. Again, this is something that Mark touched on with the offshore wind forgive me for using a acronym there, but the Offshore Wind Technical Advisory Panel. We have an interagency agreement with the National Renewable Energy Laboratory, the DOE lab, to develop what we're going to call recommended practices that will turn into eventual standards in 5 different categories, MetOcean being one of them. Next slide, please. I do not plan to go through all of these studies. It is not intended to overwhelm you, but to show you that within the last 10 years, more recent than not, these are just a handful of the atmospheric and oceanographic studies that BOEM has funded through a number of funding mechanisms, like I mentioned in the previous slides. Took a look at simulating breaking waves and estimating the loads from turbines, developed our own climatology of extreme wind, wave, and current. It would be great if we had a whole network of meteorological stations out there in the ocean in order to create this data and this climatology, but because it does not exist, as you all know, we're working with others in order to create these data sets and to establish a baseline. Prior to working with NREL and the Offshore Wind Technical Advisory Panel to develop recommended practices and eventual standards, we also funded a study to develop MetOcean characterization recommended practices for offshore wind. And so this particular study was a starting point for the interagency effort. And here are a number of others. If any of you are interested in seeing the reports, they are available online on BOEM's website under Renewable Energy Studies, or you can email me directly. My contact information will be at the end of this presentation. Next slide, please. And there we go. We are now at the end of the presentation. I look forward to taking your questions.
Thank you, Angel. I'm sure you will have given our audience a real insight into the complex chain of information needs through the life cycle of an offshore wind development. This is not a simple process, lots of stages, lots of things to think about. So now we move into our panel discussion. So if I could ask all our panelists to unmute and put in an appearance. And I would ask everyone in the audience, whilst we're going through this stage of this part of the panel discussion, if they could also, I'm sure it'll prompt lots of questions, if they could post those questions in the chat and remember to include their name and affiliation. Okay, so I'm going to start proceedings with the panel with asking them for their thoughts and views on the gaps in information needs relating to successful offshore wind energy capture in US waters, and perhaps where they know something about this, the lessons that we might learn from experience in Europe. Who would like to go first? If no one volunteers,
Yeah, and I've talked about in my presentation a lot of the data gaps. You know, it's very difficult to deploy instruments in the offshore environment. And, you know, there's 2 needs. One is the short range needs so that we can have some idea of the conditions, we can build the short range models. But there's also the need for long-term measurements in the offshore environment as well. Things like towers or buoys that are deployed over a long period of time, as well as having coastal LIDARs and such. So we can really characterize the conditions. We can capture those interesting conditions, things like nor'easters, tropical cyclones, the cold air outbreaks that I mentioned that are so important for really being able to understand how to best deploy. Now, of course, Europe has been doing a lot of research in offshore wind for a long period of time. They moved offshore because they don't have as much land area to deploy onshore as the US. And they've been doing a lot of research and deploying instruments. There's a lot of places like off Denmark, off the UK, off Germany, where they've deployed instruments for long periods of times, where they have wind farms, and we are learning from their experience. The research community works together. We share our information. When US has workshops, we certainly invite our European colleagues, as well as them inviting us to their meetings. So we're working together, and I think we're making progress in better understanding what we need to do to fill those gaps and to really enable the offshore wind industry.
I'll go ahead and add to that.
Go ahead, Angel.
So BOEM works very closely with a lot of international partners. We've recently had roundtable discussions with a number of international partners, specifically the Netherlands and Denmark. We have a memorandum of understanding with the Danish Energy Agency. And I believe we're in the process of re-upping that MOU so that we can continue to work together in the future. Some lessons learned, I'd say, well, one thing, we've learned a lot about the differences in our offshore environment. And so while there's a need to do more, or there's a benefit to the to our partners in Europe to do more of that upfront work to provide this data gathering, here in the US, the BOEM plays more of the role of the leaseholder and the regulator. And so we don't necessarily provide all that data up front, but we see the benefits. We're weighing our position in doing so.
Mark, go ahead.
One of the major challenges presently in Europe, I think, is that the appetite for offshore wind is so great that the project pipeline is hard to maintain, given the investor appetite for offshore wind, and also our need to get the energy transition moving. So one of the challenges is the timeliness of data to support the offshore wind regulatory process, because we got 2, 3, 5 years between license award and the turbines being in the water, and we need to find a way to expedite that so that we can move away from fossil fuel.
Anyone else want to pick up on this particular question?
Yeah, I can comment that we seem to be running in tandem with Europe in one aspect, which is some of the real-time monitoring of marine mammals, birds, and bats. We've actually seen some of the questions and requirements coming up through BOEM and through developers in the US, and at the same time seeing the same need arise within weeks of each other for Irish developments and Polish developments in Europe, which has been interesting that we've looked to Europe for the past decade as really advancing, but the North Atlantic right whale issue on the East Coast, as well as bird and bat issues and migratory patterns on the US Eastern Seaboard, seems to have brought it more to light as another observation required to support safe and sustainable development.
Okay, I'd like to throw in a bit of an ancillary question around this. We've heard a lot about the specific needs related to offshore wind turbines themselves. We've perhaps heard less about the data and information needs related to managing multiple uses. Now, in Europe, that's a huge issue because, we're talking about putting offshore wind installations into relatively small areas of the ocean where there are many, many other uses that they have to interact with. Would anyone like to comment on that area and the information gaps related to multiple uses as opposed to single use of the ocean?
I'll use navigation as an example here. We work with the Coast Guard to identify our wind turbines as private aids to navigation. And so, of course, shipping vessel traffic that's another use of the ocean. And we've worked with the Coast Guard to ensure that the turbines are included on nautical and navigational charts, and they meet all of the requirements for aids to navigation while out there in the ocean. And so there's an example of that there.
It's certainly in the RSC in the UK, what we've seen is that the wind farms have displaced the fishing activity, and it would be very interesting to understand what impacts that has on the fish stocks themselves. That's partly driven by the very small scale turbines that are in use. So the turbine spacing is very low. When we move to larger turbines, obviously the spacing is greater. So there may be potential for fishing within the wind farms through appropriate design of cable layouts and protection of those cables.
Carl, go ahead.
Yeah, I think we also have the art of the possible is here in front of us, because there's development yet to be done, and there's going to be power and connectivity back to shore. And so the multiple benefits from multiple data types are making my imagination go right now. And we've been talking about how to convene community players who have the different interests to have some discussion on that, because if you're going to be gathering physical data, well, you should probably consider, if it's feasible, not very much more expensive, to add biological and chemical data sets to the mix as well. And so within IUCE, we copy the integrated ocean and coastal mapping is a map once and use many times. And we say the same thing, measure once and use many times. And so there's many ways to use data and information. And if we're going to be sampling more in these spaces in the ocean where the development's going to happen, the opportunity to maximize the benefit from those data is huge. And we haven't had the conversations that we need to, I think, to determine sort of the relative trade-offs and priorities there that impact the different communities and how that will happen. And I think that at a local and regional level, and build that up to a national conversation as well.
I think that's a really interesting point, Carl, because in the UK, one of the things that we suffer from is lack of investment in ocean observing systems. And the ability to have platforms there that will reduce those costs could be very attractive.
Okay, I'm going to move us on a bit to thinking about differences in data and information needs between conventional and floating wind energy installations. I mean, clearly they're very, very different pieces of engineering. Who would like to offer some thoughts on the key differences in the data and information requirements for those two types of installation?
From my perspective, we're moving. We're sort of 10 years behind the fixed offshore wind turbines when we talk about floating. So we're really only moving to commercial scale now. So the importance of understanding the structural motions and their impact on the resource and power generation, and also the structural integrity of the system is really important. So certainly high quality wave data, wind data, and also current data will be very important. How the cables get to the seafloor is an interesting aspect. So lots of things to consider.
Yes, no, indeed, and we throw a whole new challenge into the mix as we look at floating wind as a possibility on the west coast of the US in a seismically active area. That monitoring of meteorological hazards and geophysical and geotechnical data is often not thought of in the fourth dimension of time. The geotechnical or geophysical collection might change in a few weeks, just as your metocean condition has. So I think there'll be a lot of exchange that happens in the monitoring space, both from environmental forcing, structural response, as Mark has said, but also to seismic monitoring and geological change detection.
And we also have the instances in the US where you might be putting these devices in extremely high wind regimes. So the whole issue of hurricane force winds and how that's taken account of. Sue, you were going to interject.
Ralph, and that makes a really great point. The situational awareness that's going to be needed for changes in weather and ocean conditions is just amazing, especially when we get to the floating wind turbines. Not only having good base weather forecasts where we see changes in the wind direction, speed, et cetera, but also having ocean forecasts where we can see changes in waves, how we're going to have that interaction, the fluid structural interaction in real time. So we can prepare for extreme events or big changes in power production. I think, as mentioned before, I think Mark, forecasting is going to become more important so that we can run these sorts of plants, but it's a different type of forecasting than we've had before for the onshore plants because it's beyond just wind speed. We really have to know the ocean conditions as well.
I think the importance of the digital twin becomes amplified when we move to floating structures.
Yeah. And I was involved in a very interesting discussion on this topic just earlier this week. And when you move to floating wind and extremely large structures, which are compliant, you have all the issues of how do you operate the control systems, because you've got something that when it starts moving creates a rather large rotational torque. You don't want to tear your structure apart or break your moorings. So the interaction between the wind regime and the control systems becomes a very, very complicated question. Anyone else want to add anything on this topic?
I do. In 2012 and 2015, we funded some studies to look at fatigue design and the methodology for studying this. We also looked at the loading events and those impacts on the turbine rotor, the control system, the floating platform, et cetera. Now, that was in 2012 and 2015. So at present, we have an ongoing white paper that we funded to look at current floating offshore wind projects, review ongoing research, assess the different technological issues, environmental issues, and economic issues. And we will use the results of this to better inform what's next, what data gaps still exist.
Okay, so I'm going to move on to a third question. I don't see too many questions coming in from our audience at the moment, so I may run our panel discussion a little bit further through in time. We've got 84, nearly, close to 100 people online, so I'm sure they must have some questions. Please post them in the chat. So I'm going to move on to a question about the role of public and private organizations, and specifically, how do you see the respective role of public and private organizations in delivering the data and information needs of the developing US offshore wind energy sector? So views on the role of public and private organizations. Who would like to go first?
I'll try to kick us off here. I do see the government and the regulator as creating the opportunities by making the funding opportunities available through broad agency announcements or and finding what stakeholders need to know to feel more comfortable about the advancement of offshore wind in different areas. So then there's that stakeholder engagement piece, but both of those play a role. I'd also add in there MOUs and MOAs, memorandums of agreement and understanding, working with other federal agencies or state agencies or research institutions in order to to create these opportunities for funding.
Who's next?
I can comment from the private organization side, and perhaps slightly biased with the projects and the clients I've had the luck of securing, and to call on Carl's earlier point about measuring once and using many times. We were able to take at Fugro a model that we'd used for GCUS for years, and collaborative data collection in the Gulf of Mexico, and bring that same attitude with a willing client to create data sharing. So knowing that the Rutgers University Center for Oceanography is reviewing the Maracus data and using it directly in their models from the Atlantic Shore site, does clear a lot of clutter out of the way of me delivering data to one client, and that one client packaging up on a hard drive and putting it in a secret truck to get delivered to the university researcher with 50 layers of confidentiality agreements piled in. It does really break down those barriers and allow, so not to shame too many of my other potential clients, but I would encourage that same behavior to be continued, right? It doesn't have to be the 10-minute data used for your wind resource assessment, but half-hourly data, 1 hourly subsets of the data really do go a long way in advancing ocean observations and support many other facets of the blue economy, as we've heard about today.
Anyone want to add to that? Rick, go ahead.
Yeah, building on Angel's and Ben's comments, I think you start to get at the question you asked, Ralph, by considering the fact that the taxpayers are the ultimate customers from the public perspective, and asking the question of what do they expect in terms of products and services. By way of analogy, I'll just speak for the United States, but we have determined that we will pay with public monies for our national security for the most part. So we have a publicly funded military force. The question, of course, comes down to what's the equivalent in terms of weather and ocean products. What are the foundational data and products that are part of the contract with the public to protect lives and property? From there, you expand into the tailored products, the specific products. Why should I, as a taxpayer, pay for a specifically tailored product that might be needed by a marina in Southern California? But I do believe I ought to be paying for the foundational data and products and services for public safety and protection of property. There's a fuzziness to that line, but I think that's the starting point for the discussion and the question that you asked, Rob.
And of course, there's another aspect of this, and that is where data are collected privately for proprietary private uses, to what extent you actually ensure that they eventually find their way into the public domain. I remember in the very early days of development on the European continental shelf in the oil and gas industry, Norway mandated that all data collected for whatever purpose became public. So that was a legal requirement. It's a complex question. Anyone, any views on that one?
I think most developers in Europe are comfortable with submitting data, and the Marine Data Exchange has engendered that position. The only thing they're uncomfortable about is real-time wind data, when they might be effectively bidding power forecasts into the grid and have to make a commitment that is financial in nature.
That's where they're taking that data to the bank to secure the money for the project. Yeah. So they're going to be quite reluctant to release that.
But Mark, I think you bring up a good point there, the real-time data for operations. At the same time, those data could feed back in to the observational models and provide better data assimilation so that we can have better predictions that really is good for everybody, including the folks who provided the data. So, maybe we need a trusted partner who's likely to be in the public sector to gather that data, use it in the models, but not disclose it to the competitors.
Anyone else on that topic? I can see Carl's thinking about it.
Well, I think Ben outlined the model that I know best, which is in the US, the legal framework for IUCE has non-federal entities at the regional scale who have applied to be certified for data management by NOAA. So they're catcher's mitts who can be that broker, who can be trusted and is not a profit-driven entity. And they're working to build products and services to meet customer needs. And that fuzzy line that Rick mentioned is there. At some point, if there's, companies find a market where there's monetization to be had, they'll come into that space and start to compete for the market as well. And so as Rick said earlier in his presentation, I think the market forces will teach us things as we go as well.
And of course, as we've learned in meteorology, that fuzzy line moves all the time. As technologies evolve, as needs evolve, the fuzzy line moves between what is provided publicly and what is provided privately and how those things are shared. Okay, go ahead, Mark.
I was just going to say that the efforts in the IEC Task 32 are certainly talking to this space where they're talking about standardization of all LiDAR from different types of LiDAR instrument, and making sure that it's readily accessible with a view to people adding apps on top of those data. So that certainly would help if people made those data available.
Okay, I see we've got a couple of questions coming in from the audience, so I think we'll move to those audience questions and see if we can get stimulate a few more, and I'll try and pick them off in an order that sort of fits with the flow of the discussion. And I guess the first one's a comment, and it's about the data sharing model in aviation, being AMDAR, where operators share atmospheric data in real time. And in informing model predictions help all aviation operators and the public. So there's that virtuous circle of data finding its way into the public domain and improving public good services. Another one just been mentioned, the National MESAnet program, bringing third party into NOAA's environment, respects the operator's IP rights, but gets the data into the public domain. Now I've got a specific question which completely changes tack, and I guess it's mostly going to be addressed at Sue, and that's how could the work at the small scales that you've been doing in modeling translate to other applications like hurricane predictions and areas like that? Is there some crossover in the other direction, of some of the things that are being specifically developed for offshore wind, finding application in other areas?
Oh, certainly so. There are other areas who've actually been working in the mid-ocean space for quite a long time, and we're finding collaborations with them already. Think air quality, for instance. The impact of having that coastal information makes a big difference in predicting air quality even on land. For all the uses, navigation that Angel brought up earlier, having very specific information is going to be very useful to that industry, not only in operations, but also for their own design, having more detailed information than we used to be able to develop, and models that really couple the ocean, the waves, the atmosphere all together can benefit very many applications.
Anyone else have any thoughts on that particular question?
Well, Ralph, I was just going to say that in the East Coast of the U.S., the guys at Rutgers and Maricus have determined that the cold pool that exists on the shelf and sometimes moves off the shelf and shrinks, so it's a dynamic condition, is really important for storm intensity potentially. If the cold pool is there and available for mixing, it can decelerate storm intensity. If the cold pool has been mixed by a previous storm and is not there, then you may not have any deceleration, you may have more heat available for the next storm. So that's an ocean feature that we're finding is important to try to monitor and understand and predict as it relates to hurricane intensity forecasting. And having the smaller scale sampling and analysis for a wind field, a development area, is going to teach us things about the mid-ocean conditions that are going to translate to the other application areas like that as well. It's basically a general scale scoping up comment.
An interesting question from Pam, and she's was in one of the sessions yesterday on energy policy and science, and where the topic of icing was brought up. And that's obviously an issue in offshore wind, quite a significant issue if you're somewhere where icing can occur. How much of an issue is it, and how much? What are the issues with respect to our lack of knowledge about that? Anyone anything to offer on that?
Sure, I'll go ahead on that one. I was recently on a PhD dissertation committee in Sweden that was actually looking at the impact of icing on power production. Of course, Sweden, you can imagine, it's half of the year where they have to worry about icing conditions, both onshore and offshore. And they're finding that being able to predict icing is critical. They need to know when they're going to get power out of their wind turbines and when they're not. And they're developing really forefront techniques. Now in the US, of course, we're doing research on how to forecast icing and how that information can also be used in grid management and operations. It's a very important issue, and we're moving forward on it. It certainly is going to be an issue in the Northeast US too. I think a little bit of a less of an issue than the very northern areas of Europe, just because we have the influence of the Gulf Stream on the coast of the US, but especially the Canadians are going to find those issues, and perhaps northern areas in New England as well.
Just as Sue mentioned, from BOEM's perspective, we found this is most commonly addressed in our navigational safety assessments, navigational safety risk assessment documents for offshore wind, where you take a look at icing and the potential for ice throws from turbines. What we found, like Sue mentioned, is that the occurrence of icing on the turbines isn't as frequent as you would see in other areas. So the concern is not as high. I don't dismiss it though. And what we're finding is that a number of developers are looking at, I'll say, warming technology on the blades in order to prevent this from being a significant concern and impact.
I can see a few technological issues with heating turbine blades as well, but we won't go there.
Yeah, I mean, one of the most critical areas for icing concern in the US is the Great Lakes, of course.
Yeah.
More so than the Eastern Seaboard or Western Seaboard. So there has been some consideration in the OTAP meetings that we've had. Angel, Mark, and I have been in, specifically addressing the freshwater lakes and the icing concerns there.
Okay, so I see we're 5 minutes away from the break, and I see no further questions coming in. So I think I'm going to wrap it up at this point. I think you'll all agree that this has been a fascinating and stimulating session, starting with Rick's excellent keynote address introducing the new blue economy and moving into this panel discussion on the value chain supporting the information needs of offshore wind. We've had some really useful discussions. We've only been able to touch on the needs of a single segment of the wider blue economy, but a very important one as we transition from fossil fuels to renewable energy. There's much more to explore and discuss in the future. You could envisage us having a panel discussion like this on any one of the segments in the blue economy. So on behalf of the American Meteorological Society, I thank Rick for his keynote our panelists for their introductory talks and engaging discussion, and most of all, our audience for their participation and their questions. Thank you very much, everyone.
I think if we had a chance to do a loud clap, we would certainly be clapping all the efforts that Pam and Ralph undertook to bring this panel today and the keynote. I found it very informative, and I hope all of you did as well. And you even spared us an additional 6 minutes, Ralph, that you added to the breaks if we didn't have the other. So thank you so much. We're going to come back at 4 p.m. for session 8, Truth in Science, Scientific Integrity in the Public Sphere, Mistrust, Rumors, and Risk, with 2 of my favorite people as moderators. So I'm really excited about the final session. So stick with us. We're almost done. We'll see you back here at 4. Thank you. Bye-bye.
Thank you.